I will start by reviewing some basics of conditional probability. A conditional probability can usually be identified by the phrase given or given that. For example, today isn't Saturday or Sunday, given that I'm in school. The I'm in school is a condition that affects the probability that today is not Saturday or Sunday. If the condition weren't there, we'd have to include Saturday and Sunday as possibilities for today. The probability statement, the probability that today is Tuesday given that I'm in school, has a probability 1/5 of being true, since typically I'm in school only 5 days a week. Without the condition, the statement, the probability today is Tuesday, has a probability 1/7 of being true. As you probably remember, this is how to write the probability of A given B. We know that the independence of two events is defined in terms of conditional probability. That is, events A and B are independent if and only if the probability of A is the same as the probability of A given B. We also know the general rule for multiplication. The probability of A and B is the probability of A times the probability of B given A. Remember that this becomes the probability of A and B equals the probability of A times the probability of B if A and B are independent. When we ask for the probability of A and B, we're asking for the probability that both events A and B occur. If we think of events A and B as two sets of outcomes, we're asking for the set of outcomes in the intersection of events A and B. The intersection of two sets A and B is symbolized by A intersection B. This refers to the set of elements in both set A and set B. So we could write it this way. The probability of A and B is the probability of A intersection B. Therefore, we have the following. The probability of A intersection B equals the probability of A times the probability of B given A. Or, probability of A intersection B equals probability of B times the probability of A given B. You can manipulate these statements like algebraic expressions. For instance, by dividing both sides of this statement by probability of B, we get a statement for probability of A given B. The probability of A given B is the probability of A intersection B divided by the probability of B. Let's look at an example and see how this formula works. Roll 2 dice. Let event A be roll a 1 or a 2 on the first die. Using a sample space for 2 dice, we know that 12 out of the 36 possibilities will have a 1 or 2 on the first die. So the probability of A is 12 out of 36. Let B equal 2, 3, or 4 on the second die. The probability of B is 18/36. The probability of A intersection B is 6/36. What does the probability of A given B equal? By the formula, the probability of A given B is 6/36 divided by 18/36, which is 6/18. In other words, this says that of the 18 possible outcomes in which the second die shows a 2, 3, or 4, 6 of them have a 1 or a 2 on the first die. We've also shown that the events A and B are independent, since the probability of A equals the probability of A given B.